In this video, we're going to talk about transition elements, ligands and complex ions, specifically octahedral complexes, and we'll go over using mono, bi, and hexadentate ligands to draw those, and we'll go through ways of drawing. Now, we're just going to deal with octahedral complexes in this video. We'll go on to different shape complexes in the next video. So complexes themselves, what are they? A complex is a transition metal bonded to one or more ligands. So sometimes called a central metal ion bonded to one or more ligands, but that's your definition and you will need it, so it's in green. A ligand is a molecular ion that can donate a lone pair of electrons. The really important thing is it's a lone pair of electrons to a transition metal ion, that central metal ion, and forms a dative covalent bond. Now, in transition elements, transition metals, you're going to call that a coordinate bond. Otherwise, it's called a dative covalent. Both are accepted, but a coordinate bond is what we're going to call it here. It's a very specific example. Now, the example we're going to have is with nickel. So we've got a central metal ion with nickel, okay, and then we put water with it. Now notice we're putting water like this. Now why am I putting water like that? Let's have a bit of a drawing here, just remind you of water. Okay, and we've got water with lone pairs there. Let's make those a little bit bigger. Okay, and there's your water with the lone pairs. So a ligand is a molecular ion which can donate a lone pair of electrons, there's your electrons, to a transition metal ion. So these bonds are happening because a lone pair of electrons from the oxygen is being donated to the nickel. So therefore, the element that is bonded to the central metal ion must be the one with the lone pairs. So that's why I draw it OH2. I don't want the hydrogen being bonded, it's the O that's bonded. I could draw H2O that way, but as long as the oxygen was bonded, it'll be perfect. But I'm trying to show you the two different ways you can draw it. So H2O or OH2. And we do that all the way around, and you can see there is the O each time, the O each time. Okay, and whenever we draw these, we'll draw the octahedral complex first, like the central metal ion, and then the bonds. And then we'll draw the elements that bonded, and then we add in all of the rest. But we'll go through that in the next few slides. And that is generally how you draw a complex, an octahedral complex, okay, using those central metal ion and the monodentate ligands. The last thing we do is put the charge on. So we don't do the charges within this drawing, we do it around the outside because it summarizes all the charge within. And the nickel is a 2+, and the water is neutral. So if the water is neutral, overall it will be 2+, because the nickel is 2+. And that's our final charge. We will talk about all the different examples in the next few slides. Now we're going to split the complexes into different types of ligands that make different types of drawing of those complexes. So we've got the required ligands here that you need for your specification. So really important again, you write those down in your notes, they're in green. Now we've got our definition of a ligand down here, okay, and we've got our required ligands. Now the important thing is an atom within that ligand must have lone pairs in order to make that coordinate bond. So we've got Cl-, which has that lone pair of electrons because of the gained negative there. And we've got ammonia. So it's really important you remember all these. Again, put them in your notes. Now we've got a table of other ones as well, which can come up if they introduce them. But all of these have those lone pairs. So you've got lone pair here on the oxygen, lone pair on the carbon, and a lone pair here as well for this thiocyanate. But they can be used, but they must be introduced first. These are the required ones for you to do. Now, we're quickly going to go over the octahedral complexes because we've already gone over it at the start. So any one of these, you can have 6 of these monodentate ligands because they make one coordinate bond, and that means there's 6 bonding pairs. So we have this octahedral complex. You look at how many ligands there are, and that will determine the shape of the complex. Remember, the complex is just a central metal ion surrounded by the datively bonded ligands. Now, it's the same examples that we had before. We've got those lone pairs on the water, and then we place them all around. And say that process, the bonds first, then the ligands, and we do the charge as well at the end. Now, extra thing from the last slide that I showed you is this here. So you might get the complex drawn in a kind of formula like this, or written in a formula like this, and there's an important distinction to make. If it is a ligand that's around the outside and you've got more than one, you need to put it in these rounded brackets and then say how many there are. So we've got H2O and we've got a 6. Now, in this course, you don't have to name the complexes. So this is called nickel 2-hexa-aqua, but you don't need to know that, so don't worry about naming them. But you do need to recognise them from these formula. When you apply the overall charge, because remember the nickel is 2+ and these are all neutral, so overall it is 2+, you put it in these square brackets. So once you're applying the charge, the whole thing must be surrounded by square brackets. So the ligands are surrounded by these rounded brackets, and then the whole complex is surrounded by the square brackets with the charge in the top right corner. And that's classically how you do these octahedral complexes. And most of the examples you do in your course will be on octahedral. There is a couple of other examples which we'll go over, but they're rare compared to this. Most of them will be octahedral, so practice this a lot. We're now going to talk about bidentate ligands, and bidentate ligands do 2 coordinate bonds. So monodentate does 1 coordinate bond, and bidentate does 2 coordinate bonds. So if we look here, the first example is ethane 1,2-diamine, also shortened to EN. Now that is ethane, 2 carbons, okay, diamine. So the group amine is an NH2, so we've got an NH2 on carbon number 1, and an NH2 on carbon number 2. You can shorten it to EN only if they tell you you can, okay? Otherwise, write out the full name. Now, if we draw this in skeletal formula, you can draw it in displayed if you want. It might be a good thing to stop the video and try and do that. Okay, you have 2 carbons in the centre, then the NH2, and then the NH2. Now, the important thing is there is a lone pair on this nitrogen. Because there's a lone pair on this nitrogen, it can form a coordinate bond. But there's 2 lone pairs, one on this nitrogen and one on this nitrogen, so therefore 2 coordinate bonds to the central metal ion. Remember that complex, definition of that complex is just the central metal ion coordinately bonded to ligands. The other one we do is ethane dioate, another bidentate ligand. This bidentate ligand is like dicarboxylic acid. So if you think about a carboxylic acid and think of the hydrogens removed, it can also be written as C2O42-, so good to put in your notes there so you can recognise it in a question. But it's got 2 carbons in, so we're going to draw the 2 carbons, and then it's got OO, so these are our OOs, and you can see OO. And you can see that it looks like a carboxylic acid, but it's got its hydrogen removed. Because the hydrogen has been removed as a H+, okay, this has gained an electron, and that's where that lone pair comes from, and that lone pair comes from there. So we've got 2 lone pairs, so it can be bidentate. Again, form 2 coordinate bonds. Now that means that you can look at these bidentate ligands, and this is our tip here, and there's 1 coordinate bond per lone pair. So if you look for the lone pairs that form those bonds, you can count how many coordinate bonds there are, and the total of that is the coordination number on the complex. So per bidentate ligand, you'll have 2 coordinate bonds. So if you have 3, you'll have 6 coordinate bonds, and the coordination number will be 6. And we'll show you this in the next example. So let's move that to the side and start drawing. So I'm going to give you the example, and the example we're going to use is Cu2+. Okay, and we're going to have one of these here. So we're going to start off with the ethane diamine. So if we're doing the ethane diamine, I want you to do it before me. So try and do it before me, stop the video. If you can't do it, keep watching. So what we're going to do is just draw the copper, and that's step 1. Step 2, it's an octahedral complex. It's got 6 bonds to it, and that's generally everything that's bidentate is octahedral. So we're going to go straight to octahedral. And then we draw that octahedral in terms of the bond coming out of this. Okay, and then we've also got the bond going away from us. And that's what we do. We do it that way every single time to make sure we don't make any mistakes. And then we take the ends, and we know it's going to bond through the ends, so what we can do is go N, 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 N. We know all of it bonds through the end. So if we put the element that is bonding on there straight away, then we can join it all up. So I'm going to give you an example where there's 3 bidentate, and there are different examples, that's in the next video. This is just a basic way of drawing it. And then you look at the two ends and you say, right, the two ends are bonded in between two carbons. So I'm going to draw this as displayed to give you an idea, and I'll draw another one as skeletal as well. So that's bonded to two carbons. And that is also, there's two there, so that's bonded to two carbons, and that's bonded to two carbons. And all I've done is join them up. That's all I've done, is just join them up. And then I just count how many hydrogens I've got, and I know that carbon has 4 bonds, and I know there's CH2s on there, so I just add my hydrogen. So you can draw it like this if you want. Okay, I would recommend skeletal. I'm going to do one as skeletal next. Okay, but there you have all of your hydrogens. Okay, and really important you put them all in. Now, there are all the hydrogens on the carbons. Then look and see if you've missed any hydrogens. Well, there are 2 hydrogens on each N. So therefore, notice I'm putting the hydrogens, and I can draw them out fully. I'm just going to put them in NH2. Okay, and you can see I've put them to the side of where the bond is. The bond goes to the element that I'm making the coordinate bond with, which is the one with the lone pair. Okay, and I'm going to just put all of these hydrogens on. Notice I'm just putting them out of the way of the bond, so they're not in the way. Okay, and then that will give me my full. So I've done all the nitrogens with all the right hydrogens, done all the carbons with all the right hydrogens, and I've got a full complex. The last thing I do is I draw a big bracket around it, and then I give my charge. Okay, so my charge is going to be whatever it was originally, which is 2 plus. Okay, and then I look at the ligands and see whether they're neutral or not, or they're charged. Ethane diamine is neutral. So basically that means that charge is not cancelled out by any negatives, so overall the charge is 2 plus. So this is how you draw it like this. So what we're going to do is we're going to do another example, and the other example is going to be with a different metal, but we're also going to do it skeletally, but we're going to do it with ethane dioate. Now we're going to do an example with the ethane dioate ion, and again, try and do it yourself. Okay, so just pick any transition element, doesn't really matter what it is. Okay, I'm going to pick cobalt. Okay, so I'm going to do cobalt, and I'm going to do a 3 plus on cobalt. All right, so if we just do the same process is cobalt in the center. Okay, and at the end of the day, we then do the octahedral, because we're only doing octahedral in these examples. And we put out the octahedral in the shape like this. Okay, so there's our octahedral complex. Then all we do is we do exactly the same as we did on the last one. We're going to have 3 of these. Okay, we put the O's on, because we know that's where the bond's going to happen. So O, 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 O. And then from there, we then join the O's together. We know they're joined together by a carbon and then a carbon. Okay, so these are the O's that are doing the bond. So it goes 1, 2. So 2 carbons bonding it together. So we're going to do it skeletally this time. And actually it's much quicker, okay, than the display. But you obviously do whichever version you like, okay, but this is much quicker. So we've bonded it via the 2 carbons. So we've drawn this bit here. We then do the double bonds. Okay, don't forget the double bonds. So there's your double bond there, and your double bond here, double bond here, double bond there, there's your double bond, and then there's your double bond. Okay, so we've got all our double bonds. So you do it gradually. It's not, it looks very complicated right now, but you do it gradually, and it's not so much. Now, you don't draw the charges inside here. So you don't draw the minuses on the O's or the 3 plus on the CO, because you take into account when you're doing the full charge over the whole thing. So I'm doing the full charge in my square brackets. Now, if that is the case, I do my full charge in my square brackets. I know this is 3 plus, and each one of these is a minus. So I have 6 coordinate bonds, 6 minuses. So it's 6 minus plus 3 plus, 6 minus plus 3 plus is 3 minus. So I have a 3 minus charge overall. We can also draw this, okay, like this. So we can say, okay, it's cobalt, and we know we have C2O4, okay, and we have that how many times? 1, 2, 3. So we've got that 3 times, square brackets, and we have the 3 minus. And you could get it presented to you like that, and then said, can you draw this? Okay. Or you could have said it's a cobalt 3 ion, as in cobalt 3 plus, and you have the ethane dioate ion, you have 3 of those, and you'd be expected to draw this. And that is how you can draw either skeletally or with displayed formula, and you can draw 3 bidentate ligands around a central metal ion to form an octahedral complex. The last example of octahedral we're going to go through in this video is the hexadentate ligands. Now, there's only one you really need to look at, and don't worry, you're never going to have to draw it. Okay, the only questions I've seen on this are when you have to recognise where the lone pairs are and therefore how many coordinate bonds. So, hexadentate, 6 coordinate bonds, and again octahedral like we've been doing all the way through, and it is this thing called EDTA. It's derived from ethylene diamine tetraacetic acid, see the EDTA. Now it looks like this. Now that looks horrendous, okay, and very, very difficult to reproduce, so don't worry, you're never going to have to draw it. But if you get given it in the exam, and here's the structure, look for where those negative charges are. Those are where the lone pairs are, okay, and that's where you'll form coordinate bonds. But that would be a wrong answer to say there's 4. Remember there's 6. So where else can you see the lone pairs? Well, the other lone pairs are going to be in these nitrogens in the centre. So there's the 4 lone pairs to start off with on the negatives, and then you've got those extra 2 on those nitrogens. So it can form 6 coordinate bonds, and it forms a really complex looking thing like this. But don't worry about that, okay? That is, you're not going to have to draw it, and do not worry about it. And you can see here the negatives are included. We wouldn't normally include the negative, and we're not talking about the overall charge on this. Literally, that's because you just have to recognise that it's 6, and you just have to recognise that there are lone pairs that form those coordinate bonds. Now, what is EDTA used for? So, first of all, you have those 6 coordinate bonds, and you have to know that they're at the lone pairs. But it's used as a chelating agent. So chelating means kind of crab claw like that. If you look up the word chelate, it's like a crab claw. What it does, it binds to the metal like this, surrounds them, and then takes it out of your body, and then you urinate and you get rid of it. And it decreases the concentration of that ion in the solution. Okay, just takes it out by binding it in, and then obviously you get rid of it. And then that lowers the amount of metal in your system. And it's a way of treating people who have a disproportionate amount of certain metals in their system. And that is how you do hexadentate ligands, and the only one you're going to have to do is EDTA.